Right. Okay. So yesterday we have discussed about the solution procedure of the system of differential equations, right? And then we have also looking about the long-term behavior of the system, right? So we discussed 2 by 2 and then we started 3 by 3 and then, yeah. So this is yesterday what we discussed about the 3 by 3 system of the differential equation. Right. So this is my system of differential equation. This is x prime is equals to ax, right? Where A is the 3 by 3 matrix. And the initial condition at t is equals to 0 is 1, 0, 3, right? So this is 1 is x1, x01 or x10, what we are using the notation, and this is x02 or x03, etc. And we took the determinant of a minus lambda I, right? This is our ai, and ai minus lambda I determinant, that is you will get the, that is the determinant of minus 5 minus lambda 0 to 0 minus 3 minus lambda minus 4 and 0 minus 1 minus 3 minus lambda. So this is, if you expanding determinant, then you will get the characteristic equation, and you have to solve those equations. You will get lambda is equals to minus 5 and lambda is equals to minus 3 plus or minus 2. So here is the eigenvalues, lambda 1, lambda 2 is equals to minus 5 because it is a repeated one, right? Is it repeated?
Yes, it is repeated.
Okay, right. And lambda 3 is equals to minus 1, right? So the corresponding eigenvalues, lambda 1 is equals to minus 5. So this is the repeated one. So we are taking V1 is equals to a vector V1, V12, V13. And suppose that this one is equals to 0. So we need to identify the eigenvector corresponding the eigenvalue lambda 1 is equals to minus 5. So a minus lambda 1 times I V1 is equals to 0. This is the lambda 1 I, right? So here is V1, 1, V12, V13. So expanding this one, right? So that is minus V12 plus 2 V13 is equals to 0 because the right hand side is the 0 vector 0, 0. And second equation, when we expanding that one, 2 V13 is equals to 0, right? So when we 2 V13 is equals to 0 mean V13 is equals to 0. Substitute in the first equation, you will get V12 is also 0. So what happened? We got V12 and V13 are equals to 0. So which one is arbitrary element in that vector? V1. So this is our choice. So you can take V1 is equals to 1, 1. So when we are taking V1 is equals to 1, then your vector V1 is equals to 1, 0, 0. And what is the solution? The solution is x1 of t is equals to, what is that one? E to the power of minus 5t times v1. v1 is, that is 1, 0, 0, right? And see, yesterday I was explaining in rushing because the last minute we reach this one. And so just to recall that one, once if the eigenvalue is repeated a k times, then V1, we will identify what is the procedure of the previous one. Then we need to uh, find out the hidden vectors V2, V3, and so on, Vk. Of course, in this case, there are two. Our case is only I is equals to 2, right? So we can take this one, A minus lambda I whole square times V2 is equals to 0, and A minus lambda I to the power of I minus 1, that is a 2 minus 1, and V2 is not equals to 0. Then the solution is simple in this way. Right. So our eigenvalue is repeated 2 times. So that's why I am going to take A minus lambda 1 I whole square is equals to, already we know that what is the lambda 1 I in the previous one, or already this is, right? So just you are the multiply with that the same vector. So vector multiplication, the product of two vectors, and you know that how to multiply. So this is the 3 by 3 size, this is the 3 by 3 size. It is possible to multiply to each other. So the first row and first column 0 times 0, everything everyone knows, plus 0 into 0 plus 2 into 0. I think you will get all zeros. That is the 0. And the second one minus 2, the first row into second column, that is 0 into 0 plus 0 into 2 times plus the last one, 2 times minus 1. So that is minus 2. So this is minus. So similarly, you can apply that procedure what you learn in your linear algebra. So you will get the equation, right? So here also simple, we can make it a 0, 0, the last one, because here see, this is the double, this R3 is equals to 2 times of R1, and R2 is the 2 times of R3. So it is easy to getting a row echelon form to make all these zeros. So finally you got 0 minus 2, 4. And then you have to consider the second vector, V2 is equals to V21, V22, V23. And here, this is our lambda square, lambda 1 I square, V2 is equals to 0. And make sure this one is not equals to 0. That is A minus lambda 1 I V2 is equals to 0. This is the condition. So you have to careful the condition. So based on this one, this one, you have to multiply here is V21, V22, V23, right? So you will get only V21 is 0, and then you will get minus 2 V22 plus 4 V23 is equals to 0. This is. So then V2 is equals to 2V23. So what is that value? You can consider V23 is equals to 1, and you will get V22 is equals to 2, right? So then what is your V21? That is your choice. that is an arbitrary. So U21, you can consider 1, but you have to careful already in previous vector, we are assuming V1 is equals to 1. So here we try to avoid to take again 1, but because to protect this condition. So that's why I can take 0. So that's why V21 is equals to 0 in this case. So totally the vector is, I think, 0, 1, and 2, right? So then your solution, the x2 solution, the x2 solution is in this way. So here is x2 of t is equals to e to the power of minus 5t times I plus, I is here 3 by 3 identity matrix, t times a minus lambda I times b. This is. So that is what you are getting here, right? So this is a simple matrix multiplication of the uh, two matrices. Is the size of the uh, 3 by 1. This is 3 by 3. So then after simplification, you will get this is a solution, the second solution, right? And you can see the last one in the same way. So there is no repeated, you can find easily. So this is your lambda 3i. So you can make it this one as a row echelon form. Again here, see this is a, that's why what I am saying in class. The 3 by 3 matrix is a very simple because it is easily reducible to get the row echelon form. See here, here is the row 3 is equals to 2 times uh, row 2. So we can easily make it a 0 of the last rows. So totally this is your matrix. So we need to find vector V3. For that one, we are choosing V3 is equals to V31, V32, V33, such that the A minus lambda 3i times V3 is equals to 0. So just you have to make it multiply here is V31, V32, V33, right? So you will get the minus 4 times V31 plus 2V33 is equals to 0 and minus 2V32 minus 4V33 is equals to 0, right? So of course we can simplify here is V32 is equals to minus V32 is equals to 2V33, right? So when we choose V3 is equals to 1, then you will get V32 is equals to minus 2. Or whatever the possibilities, you can verify that one, right? So here V33 is equals to 2. Of course, the minus plus, no problem. Based on that one, I choose here, but here is different choice, right? Minus 2V33, 4V3. Here is minus 4V31. V31 is equals to 1 by 2 V33 and V3 is equals to minus 2V3, right? So this is your final vector V3 and your solution is this one. So totally this is the general solution x of t is equals to C1 x1 of t plus C2 x2 of t plus C3 x3 of t. So you have a 3 constants. So you know that how do we get that one by using the initial condition. So already we know that what is the initial condition. The initial condition of this problem is 103. So using 103, we will get this is equals to 103 and equating the corresponding equations. Again, I did here this is, that one, right? So this matrix 1, 0, 1, 1, 1, minus 4, 0, 2, 2, and the right hand side is 1, 0, 3. So again, apply the row echelon form, right? To make the possible zeros of the diagonal entries below the diagonal entries. Here I did only one operation. I apply the operation on R3, right? So that is R3 minus 2R2. You will get this equation, right? This is for the related to the what is that values, and C1, C2, C3, and then the corresponding values are 1, 0, 3. So for example, in the first one, what is that one? C1 plus C3 is equals to 1. In the second one, C2 minus 4C3 is equals to 0. The last one is 10C3 is equals to 3. Right? So this implies C3 is equals to 3 by 10. Right? Of course, substitute 3 by 10 in the second equation, you will get the C2. And also substitute C3 value in the first equation, you will get the C1. So substitute those C1, C2, C3 in your general solution, you will get the analytical solution. Right? So here see, what is the mechanism? What is the long time behavior? So here is e to the power of minus 5t. Here is e to the power of minus t. Right? Isn't it? So what happened as here is, of course, when you substitute, here is again t times minus 5 to t. See, 5 to the power of minus 5 to tends to 0 as t tends to infinity. Then if you multiply with t, is again approaches to 0 as t tends to infinity. So what happened? If you take the limit t tends to infinity x of t, the right hand side of the analytical solution, what will happen? The value is going to the 0, 0 vector. Right? So in previous example, so it doesn't tends to 0, 0. Right? So keep in your mind that one is useful for discussion. Right? So what is that one? The long-term behavior of the linear system is dependent on the sign of the eigenvalues. So in our problem, eigenvalues are lambda 1 is equals to lambda 2 is equals to minus 5. And lambda 3 is equals to minus 1. What is the sign of this one? This is a minus 1, here is a minus 1. So that's why the limit as t tends to infinity, all solutions are approaches to 0. Suppose if one solution is suppose minus alpha and lambda 2 is equals to some positive, then your behavior, the long-term behavior does not approaches to 0, 0 there. Right? So that is, you can see the first example, that solution increasing in magnitude without bound over the times, since one of the eigenvalue is positive. Right? So based on these eigenvalues, now we are going to discuss the stability of the continuous of the dynamical system. Right? Right. Now, as usual, what we discuss the equilibrium point in the um, discrete system. Here also the same scenario. After that, we are getting to the Jacobian matrix also. First, we will see how do we get the equilibrium points and what is the link, the stability link with the stability analysis of our dynamical system, right? So, let us see, this is my continuous autonomous dynamical system dx dt is equals to f of x with initial condition at t naught is equals to x naught. So now, for this dynamical system, I am going to say the vector x star is an equilibrium point of the system for this one. If the right hand side, the f of x, if you replace x by x star and then equals to 0. So the point x star, the vector x star is said to be an equilibrium point. The condition is f of x star is equals to, see for example. So this is my dynamical system. And of course, in place of f of x is equals to ax, that is my 2 by 2 matrix, 1 minus 1 minus 4, 1. That is what we discussed in the first example, right? And suppose that x star is equals to x1 star and x2 star. This is my equilibrium point. Then I am going to say this is an equilibrium point for the system. So what is the right hand side? Right hand side is equals to f of x is equals to ax. So f of x star, that is ax star, should be equals to 0. That is 1 minus 1 minus 4 1 times you can say x1 star and x2 star is equals to 0. Right? So what is this one? When is a simplification, x1 star minus x2 star is equals to 0 and minus 4x1 star plus x2 star is equals to 0. What is here? X1 star is equals to x2 star, right? So substitute that one in this one. What happened? This is minus 4x2 star plus x2 star is equals to 0. That implies minus 3x2 star is equals to 0, implies x2 star is equals to 0. So in the first equation, x1 star is equals to x2 star. Therefore, x1 star is also equals to 0. So totally, what is your equilibrium point? My equilibrium point, x star is equals to x1 star, x2 star transpose. That is simply a 0, 0. So this is my equilibrium point for this dynamical system. So similarly, let us say this is our second example 3 by 3, what we discussed just now. This is my AX, right? So as usual, you have to multiply the x star. I'm going to say equilibrium point, that is AX star is equals to 0. That is, you will get the equations, right? 2x1 star plus x3 is equals to 0. The second one, 2x2 star minus x3 star is equals to 0. Of course, we can make this one is a 0, what we did previous by using the row operation. So that's why I didn't take the last one, right? So from this one, so you can calculate from here, the x1 star is equals to minus x3 star over 2. And here is x2 star is equals to x3 star over, right? So x1 star, x2 star, is equals to, right. So what is the x3 star? Just I am taking an arbitrary. If I am taking x3 is equals to x3 star is equals to 2, then 2 by 2 is equals to 1 here, and here is minus 2 by 2 is equals to minus 1. So the equilibrium point x star is equals to minus 1, 1, and 2, right? So x3 is any real number, right? So this is the way to identify the equilibrium point. So what is the use of this equilibrium point for our stability analysis? So here there is one theorem, the same way what we discussed in the uh, dynamical system of the uh, discrete system of the equation. So this is my dynamical system, dx dt is equals to ax, and x of t naught is equals to x naught, right? So the equilibrium point x star is equals to 0. Why I am taking x star is equals to 0? Why I am taking here also x, why the x star is equals to 0, but in previous example, this is not equals to 0. But before example, this is a 0, right? The x star is here is a 0, but in this equation is non-zero. So remember that the equilibrium point, there are three possibilities, right? So equilibrium point may or may not be exist. If it is exist, it is an 1 and more than 1, right? So here is, I am emphasize only for the 0 equilibrium point. So what is that meaning? So what about the non-zero? X star is a non-zero vector. Okay. So according to this one, we got a non-zero. For example, what about the zero vector? Let us say x star is again another 0. That is a 0 vector. What will happen when we substitute, when we substitute in place of x here 0, 0, then you will get 0, 0, 0, right? So what is that meaning? Here also 0, 0 is also equilibrium point. But here we calculated according to the matrix. We didn't consider that one, but it is already exist. But for simplification, we got it is a non-zero, right? So what is the conclusion? What I am going to say? For any autonomous system of the form, oh my God, how do we Yes, here is possible, but I am not able to. Mm. So one second. Right. Okay. So what is my conclusion? In any autonomous system of the form that is dx dt ax is equals to dx dt is equals to ax, such an autonomous system, the zero equilibrium point is always exist. There is no doubt about it. So that's why I call this here the equilibrium point x star is equals to 0, right? Existence for the autonomous system of the form, right? So even though if it is other non-zero equilibrium point may or may not be exist, but there is a guarantee for the existence of equilibrium point 0, 0 for this autonomous system. So that's why the theorem tells us the zero equilibrium point of the system is asymptotically stable. What is the condition? If all eigenvalues have a negative real parts, right? So even either complex or real, I told you yesterday, for real numbers also can be written as complex number. For example, in previous, I can write -5 is equals to -5 plus 0i. So what is the real part of this number? Real part of this one is equals to this complex number. Let us say x or z. The real part of z is equals to -5. So if all eigenvalues have a negative real part, then the system is asymptotically stable. And otherwise, that is one of the eigenvalue has a positive real part, at least one positive, then the system is unstable. So that's why in our previous example 3 by 3 system, those eigenvalues are all negative. So that's why the long-term behavior tends to 0. So that's why the system is asymptotically stable. And before that one, that is 2 by 2 matrix, for that one is a positive and one is the negative. So that's why the system is unstable. Is any doubt for that one? So here you can see, this is what I am explaining. This is our example, previous example. For this one, eigenvalues are lambda 1 is equals to -1 and lambda 2 is equals to +3. So for this one, there is a equilibrium point x star. So this equilibrium point x star is equals to 0 is unstable because your eigenvalue lambda 2 is equals to 3, which is greater than 0. And similarly, the second example, we know that lambda 1, lambda 2 is -5 and lambda 3 is equals to -1. So all eigenvalue real parts are negative. Then we can say uh, we can say that one is uh, what is that one? The long-term behavior is also tends to 0. Your x of t limit t tends to 0 is equals to 0. And also your system is asymptotically stable, right? Okay, right. So there is one stability criterion for the continuous dynamical system, right? Because we have identified equilibrium point for the autonomous system x star is equals to ax. But sometimes it is difficult to convert it into a f of x is equals to ax. So we will get only vector form f of x. In such a case, what is the mechanism to identify the stability criteria, right? So of course, already we discussed this type for the discrete dynamical system. So here also same way we will see. So that is the possibility of such a that where we are unable to getting that matrix that is possible for the non-linear, right? For non-linear autonomous system, we cannot find a equivalent matrix A, right? So in such a case, we are using the Jacobian matrix here. So this is my dynamical system, dx dt is equals to f of x, and x of t naught is equals to x naught, okay? Suppose my x star, that is x1 star and so on, xn star transpose, I am going to say, is an equilibrium point of this dynamical system, okay? So it is easy to get the equilibrium point, that is the meaning of f of x star is equals to 0. So substitute x star and make it is equals to 0, then find the corresponding what is the x1, x2, x3, etc. Right? But here keep in your mind, there is no guarantee of the zero equilibrium for this system because it is a non-linear, may or may not be exist. Are you catch my point? For this previous linear autonomous system, there is a guarantee for the zero equilibrium point, but here is may or may not be exist. So whatever it may be, when we are substitute x star and make it equating 0, then whatever the values of your x1 star, x2 star, that is your equilibrium point. Okay, right? No problem. So what we are going to do, then the J of the Jacobian matrix I am going to construct with respect to the equilibrium point. That is nothing but a matrix. What is the matrix? J of x star is equals to Jij x star. So what is this Jij x star? Is nothing but the left hand side, the derivative of dou f, this is your f of x mean you will get f of x1, f of x2, right? So that is dou f phi by dou x j, right? So dou f by dou x j of x star, sorry, x star for I is equals to, for I comma j is equals to 1, 2 and so on, n, right? So when we are constructing this Jacobian matrix, you can say that matrix as A as usual. Then you can apply the previous one. What is the previous one? The equilibrium point x star is asymptotically stable if all eigenvalues of j of x star have a negative real part. Same what we discussed for the linear system. In the linear system, we are discussing only for x dot x x prime, that is a dx dt is equals to ax. For this matrix we are applying. But whereas a non-linear autonomous dynamical system, of course, this is also applicable for the linear autonomous system, but a waste. right? Because once if you have an eigenvalue, we can determine, right? For this case, what we are going to, we need to construct a Jacobian. Jacobian is obtain these entries of the Jacobian matrix. This is the formula. Suppose the equilibrium point x star is unstable if the eigenvalues, at least one should be a positive real part. So we will see one example, of course. So here is once if you are thinking the Jacobian matrix, even in the dynamical system, then of course, even for the previous section, that is a first order differential equation, we are using the what is that? Directional derivatives, that is arrows. But here we are using the phase portrait. So what is the phase portrait? We will see, right? Why phase portrait we are using, right? Here is if the condition is, if the neither condition 1 and 2 in theorem 6.2.5, that is what we discussed now here, right, are not satisfied for a given system, then no conclusion can be drawn from this theorem, right? So in such a case, what we are going to investigate, like in previous chapter, we are identify the directional derivatives, that is arrows, arrow vectors, right? Based on that arrow vectors, when the all arrows moving towards the equilibrium point, we call it what we call, that is a sink, right? And similarly, what all arrows are moves away from the equilibrium point, we call it a sink, right? And also we discussed about what is the center, right? Of course, that is unstable. We call it a source, unstable source, and a stable center, right? So same such a patterns we can use. Here the MATLAB is essential for you. So here construct the phase portraits. So in previous chapter, we are using just to directional derivatives, but here there are system of equations, especially for the case of two equations, because it is a visualize for the two that is x1 and x2, right? So this is the one is the dx1 by dt and dx2 by dt is equals to f2 x1 2. So for this system of two equation, we are going to construct the following plots. The vector arrow plot with the normalized directional components. Of course, you know that one. How do we normalize the given vector, right? So this is f1 x1 over some norm. What is the norm? Norm is here the square root of f1 x1 2 whole square plus the second one square. So this is a norm, right? That is in r square. We call it a Euclidean norm, right? So the people who are studying the 3277 real analysis, the people knows very well. Even the linear algebra, advanced linear algebra, or even you can see 2273. So those vector plot, we are going to find the normalized directional components which are obtained this one, number one. Number two, after finding the arrows, we are going to, yeah. So we are going to plot the graphs we are going to construct the plot. One is x1 of t and second one is x2 of t, right? For the initial values x0 of x1, right? So sometimes we compute these values by using numerical methods, what we discussed in the first part, that is a dynamical system. What is the Euler's method? That is also can be used for different values of t. So how do we analyze those plots, the phase portraits plots? So same. So your equilibrium point x star move in towards x star, that is an equilibrium point from all directions, because here is a two-dimensional, either up or down, whatever the direction. In all directions, these arrows, for example, this is your x naught star, sorry, x star. So all arrows are moving towards the your equilibrium point, then that is called the asymptotically stable, and we call it sink. And all arrows x star move away from x star in all directions, then the point x star is called unstable. That is called source unstable. Sometimes the arrows x star produce an orbit around x star, right? Suppose the lines, the moving, the circles like this one. So such a cases we can see that one is a stable center. But remember that such a case that is never be asymptotically stable. So what is the other possibilities? Sometimes arrows are moves towards x star, and other arrows moves away from the equilibrium point. In such a case, that is called unstable saddle point, right? So this is what we discussed previous section. The same can be applied here, but here we are using the plots. X1 is x direction and x2 is a y direction. And using, sometimes we can use the Euler method for this one, right? Okay, so I need a 5 to 10 minutes break, then we can join after that. So 1 hour is completed. So I need some 5 to 10, 5 to 6 minutes. So now it is 8:05. I will come back 8, yeah, 10, right? Okay. So now I am stopping the share and then I will open again. Or I can stop the, what is this one? Cloud recording. Stop the recording.